Okay, well, I'm going to concentrate on the fusion end of our work. I can come back another time to discuss the Big Bang, or we can discuss it during the questions. But we've got a full schedule just discussing fusion. So, as I say, what we're talking about is fusion as humanity's way forward. So, right now, humanity, all of us, is in crisis. Ever since the pandemic, and really developing for a long way back, the dynamism and development of the world economy has been slowing down and going into reverse. This is a graph of the blue line showing the rate of mortality decline globally of humanity. So the higher the rate of decline, the faster humanity's standard of living was advancing. And you see, back in the 1960s, this was the peak of the post-war boom, when the level of standard of living globally was advancing very rapidly. But then it started to slow during the 80s and 90s. There was a little bump during the first decade of this century. And then moving into the pandemic, there has been a shift to negative growth, to a rise in the death rate. If we look at the energy situation, the rate of energy increase of the entire world has almost matched that general tendency of the standard of living. A very rapid rise during the 60s, then a slowing in the 70s and 80s, and now a collapse in the past decade. So the political and economic crises that we are experiencing right now are basically summarized in these two graphs. In order for humanity to move forward, we have to triple energy production and return to the growth rates of the 60s or beyond. That's not the only thing we have to do to escape the crisis, but without a growth of an energy, we can't escape the crisis. We don't have the resources to give people the growth in standard of living that provides hope for everyone. We can't do that with fossil fuels. Fossil fuels right now are a major source of the increase in the death rate. This is global deaths per trillion kilowatt hours of various energy sources. And simply due to pollution, you see coal, oil, and biomass, which is just a fancy word for continuing wood burning, to be a source of enormous mortality rates. Right now, there are 7 million deaths due to fossil fuel air pollution every year. 7 million, approximately equal to the deaths from at the height of the pandemic. Every decade, the same number of dead from fossil fuel pollution as from the Second World War. At the same time, totally ignoring the question of climate warming, the emission of the consumption of fossil fuels is one of the major drags on the world economy. Cost of fossil fuels today is $5 trillion per year, equally to half of the global manufacturing output, that of the United States, China, and Japan combined. Setting aside the question of global warming, the CO2 levels that will be emitted if we relied on fossil fuels to give us the energy growth we need would produce a CO2 level of 600 parts per million, this green line, which is an increase in CO2 beyond anything that the world has seen since 25 million years ago. So 25 million years ago, the development of widespread grasslands drove the CO2 level down significantly, which not only changed climate radically, but it also gave rise to more efficient respiration in all animals, including our ancestors, which in no way had developed by 25 million years ago, our ancestors' ancestors. So to raise CO2 levels to 600 parts per million would be an uncontrolled experiment with all animal life. So if we can't use fossil fuels, what can we use? Well, history has shown that for energy use to advance, we need cheap, clean, safe, unlimited energy. And this means higher energy density. That is, energy density energy sources where we get more energy production from less area and from less mass. So what does that look like? Industrialization went on going from wood to coal and oil and gas. These cubes represent the same amount of energy as 10,000 tons of wood. So coal was the first step away from wood, was an increase of approximately 60%. Another increase in 60% in energy density was to oil and gas. These seemingly small changes in energy density gave rise to tremendous increases in productivity, because not only were these denser sources of fuel, they were more available, they were more transformable. So that's, again, what we have to do today. So if that's what we have to do today, we can't rely on solar and wind. Solar and wind are too low density. They take up too much room. They are too expensive per unit energy production. To give an example, this is the area of southern Connecticut, lower and mid Hudson Valley, Long Island, and New York City that would have to be covered with continuous solar panels in order to provide all the energy needs for New York City alone. There is a huge difference in the cost for baseload power, for 24/7 power, than for the way solar and wind are being used today, which is supplement when the sun is shining and when the wind is blowing. So right now, the cost for solar when the sun shines is about $1 per watt. But if you add in the cost of energy storage to provide round-the-clock solar energy, it would be $10 per watt invested money. And if you have to supply solar year-round, it rises to $30 per watt. This is another way of looking at it. These little blue squares indicate the amount of space needed to provide 1 billion kilowatt hours per year continuous energy. And as you can see, solar and wind actually take up far more space than existing energy sources, coal and gas and nuclear. The only way we can go forward is to use fusion energy. Fusion energy, which is the energy that powers the sun and all the stars in the universe, is the densest form of energy available to us, 1 million times denser than fossil. So if you look very closely, you can see here, this little red dot represents the 1 ton of uranium that is the equivalent of 10,000 tons of wood. But looking even more closely, you see this tiny dot of 5 kilograms of PB11, hydrogen-boron fusion fuel, 5 kilograms of fusion fuel produces the same energy as 1 ton of uranium or 10,000 tons of wood. So that's the energy source that we have to use going forward. The sort of fusion energy we're developing here at LPPFusion is extremely compact. For the energy that we were discussing, 1 billion kilowatt hours per year, we would need 20 of our focus fusion generators. They would take up 320 square meters of space, or 1/8,000th of a square mile, compared with the many, many square miles needed for existing energy sources. So this just gives you an example of shrinking our little generator and comparing it with the solar and wind sources that would produce the same amount of year-round power. So hydrogen-boron is to the next epoch of human development, the new oil. This amount of hydrogen-boron fuel, 100 grams, which we have in our own lab, is the equivalent of 2 tankers, 76 tons of oil. And of course, extreme high energy density leads to extremely low cost. This is a comparison of dollars per million BTU, another way of measuring energy, of solar, fission, wind, oil, hydro, natural gas, coal, and what we have calculated our focus fusion generators to cost. Basically, they would cost about a factor of 6 to 10 below any source of energy today. That's what we're aiming for. And this is a totally different approach to fusion than those that you have heard about and read about. The National Ignition Facility, for example, the huge laser facility that recently achieved new records in fusion output, is the size of several football fields. The ITER tokamak, which is under construction and has been under construction for some time in France, you can barely see the little man. You can't really see the little man, who is half the size of my arrow, representing the size of this gigantic machine. But our machine is 4 meters on a side, fits in a room 4 meters on a side, and the heart of the machine can be held in your hands, the electrodes. So before I go on to discuss what focus fusion, our approach to fusion, is about, let me break here for just a couple of questions, and then I'll give the rest of the presentation and we can have the general discussion. So Joe, do you want to see whether anybody has a couple of questions on the presentation so far?
Nothing, Eric. Why don't you continue?
Okay, you want me to go to the end? That's fine.
Go ahead.
No.
Continue. Yes.
Okay. So what are we talking about when we say focus fusion? Well, our device, the dense plasma focus device running on hydrogen-boron fuel, that combination is what we call focus fusion. That's our approach to fusion energy. Now, let me focus first on the hydrogen-boron fuel. Hydrogen-boron fuel has been known for decades to be the ideal fusion fuel. And this is what it looks like in nuclear models. So you have a proton, which is the nucleus of hydrogen, the most abundant element in the universe, and of course, one of the most abundant on Earth, since a constituent of water. So the proton collides at high temperature with a boron nucleus. Boron is also a fairly common element, both can be mined from the ground and is also a constituent of sea salt. So when the proton and the boron combine, they briefly form an unstable carbon atom and split up into 3 helium nuclei, which scientists also call alpha particles. So you get no neutrons out of this, no radioactive waste. All you get is useful helium. Now, why is that important? It's important for several reasons. One is, as I say, your fuel is cheap and extremely abundant. There's no possibility of a OPEC for hydrogen boron fuel. The amount of boron that is currently mined is 10 times the amount that would be needed to fuel all of our energy needs with hydrogen-boron fusion fuel. And there's more of it in sea salt. Hydrogen, again, comes from water. You have, again, no nuclear waste. If you have no neutrons, neutrons are what produce radioactive waste by transmuting other materials into radioactive materials. That doesn't happen. There will be no radioactive waste. Small amount of very short-lived radioactive materials are produced during the running of the device by secondary reactions. But when you turn the device off, within 10 hours, you can enter the, open up the device without any precautions. Equally important, because you are producing energy in the form of moving charged particles, you don't need to produce heat to produce steam to drive a turbine and generator, all of which is very expensive. You can convert directly into electricity, and I'll explain at the end how we do that. So that's an enormous savings and can make the process far cheaper than any existing energy source. We're not the only one who are looking at hydrogen boron fuel. Other companies such as TAE, Marvel, and HB11 have started experimenting with this fuel using different devices, mainly with lasers. The other aspect of our approach is the device we use, which is called a dense plasma focus device. And again, this is an extremely compact device. This is approximately the size of what a generator will be, and it's also about the size of our existing experimental device, which is we call Focus Fusion 2B. The reason we can have a much smaller device, and we've only spent $10 million developing it instead of $1 billion, is we imitate nature. We use the natural instabilities in plasmas, the ability of the plasmas to form filaments through the pinch effect to heat and compress the plasma. Most of our colleagues in fusion, most of the work you've heard about in fusion, they're trying to fight these instabilities to make the plasma stable. And that's just very, very difficult, near impossible. Instead, like the Wright brothers imitating birds, we're imitating these filaments that exist on all scales throughout the universe, in solar flares, in beams from the formation of stars in quasars and spiral galaxies. We've shrunk these filaments down to laboratory size, and as a result, we get the ability to create temperatures of billions of degrees in devices that are only centimeters apart across. So let me show you just briefly how the device works. We have the device within a vacuum chamber. And within the vacuum chamber are a cathode and an anode, which are only a few centimeters across. So in step one, we have energy stored in a capacitor bank. And in a few microseconds, we release that energy through switches across these, the gap between the cathode, which is the outer ring, and the anode, which is the inner ring. So this produces filaments of plasma, which is electrically conducting gas, which is carrying almost 2 megaamps, 2 million amps of current in this very small centimeter wide space. The forces that are produced by the electric currents and the magnetic fields they produce drive these filaments down the end of the anode, which is only about 10 centimeters long. So the filaments funnel together into a hole in the anode, and then a second example of the pinch effect, which attracts filaments of current together, merges these currents into a single filament. So the density of energy has become much higher. Now this filament kinks up like an old wire to a landline, if any of you still have landlines. And the pinch effect pinches this into a self-contained, whoops, sorry. Click the wrong button. Into a self-contained plasma ball, which we call a plasmoid. That plasmoid shrinks down to only microns. So all the energy that was in the capacitors is shrunk to this small dimension. And in the process, plasmoid heats up to billions of degrees, hundreds of times more than the temperature in the center of the sun. So this causes the fusion reactions to occur. So that's basically how we've been producing fusion so far, not with PB11, with deuterium, which is an isotope of hydrogen and is simpler to work with. But we have demonstrated and published in peer-reviewed papers these enormous temperatures. And we've published these results in peer-reviewed journals, journals reviewed by our competitors. So as we say in this paper we published last year, so far our project has led to the achievement of the highest confined ion energies of any fusion experiment, the lowest impurities, and among privately funded commercial fusion efforts, our experiments have achieved the highest ratio of fusion energy generation to device energy input. So that's what we're trying to achieve. We're trying to achieve more energy out of the device than in. We haven't achieved that yet, but we've gotten closer than any other private fusion company. Now, how do we get the energy out? I can just describe briefly how the energy gets out, and I'll turn it over to my alter ego to describe it in this little animation. Most of the fusion energies and most of the energy originally fed into the device is emitted with an ion beam. Can people hear the narration? Wave your hand if you can hear. Okay. Traveling away from the electron. This beam is fed through a type of induction core. The ion beam generates changing magnetic fields, which in turn generate current in the core. This pulse of current is fed to the capacitor. Some of that energy is recycled to provide energy for the next shock, and the rest is fed out to the grid. An additional part of the fusion energy is emitted as impulsive X-rays. This is captured in an onion-like photoelectric device. X-rays collide with electrons in thin metal film, causing the electrons to be emitted with high energy. The electrons are captured on charged electrical grids, generating current that is also fed to the grid. So in this way, we're able to get the energy out of the device with a very compact direct energy transformer, potentially much cheaper than the turbines that are used in today's energy sources. Most of the fusion. So where are we now? Right now, we still have to raise additional money to complete the research phase. We hope this year in our program. So the research phase will be completed when we prove that we can get net energy out of the device. Within about 3 months, we're going to start running with hydrogen-boron fuel, which we have in our lab. So right now, this is an ad from the sponsor. We're raising money from the general public through crowd sharing. We've previously raised $10 million, and this is available to anybody through the WeFunder crowdfunding platform, or to larger investors through direct investment. If we can raise $2 million this year, we expect to complete the research, get net energy. If we can raise approximately $100 million for the development phase, we think we could complete the development phase and get a working prototype generator by the year 2028. And as I say, this is not based just on our say-so. We've published in the literature peer-reviewed research that shows that we are in the lead among private fusion companies. The development of this energy source in this decade could allow the replacement of all fossil fuel generation before the middle of this century, by about 2045 or 2050, because the amount of money involved in investing in these energy sources would be 10 times less than the amount of money now being invested in existing energy sources. This would revolutionize life here on Earth, would allow money now spent for energy to go for infrastructure, to go for housing, to go for education, to go for clean water. This would be able to provide a decent standard of living, not only for us in the United States and Europe, but for the entire planet. It would end the crisis that humanity is facing, or at least make possible that end. So that's what we're trying to do. And I thank you for your attention, and I'll be open to questions.